Now let's ask a very basic question. You are sitting, I assume, in a room filled with air, unless you're doing this on a space shuttle or something like that. And how fast are those air molecules around you going at? Well, the motion of an air molecule could be in the x, y, and z directions. Each of those has an energy of about half kT, so the total motion energy is going to be about 3/2 kT. There's also going to be vibration and rotation, but it's the motion we're interested in here. Now that's going to be equal to the kinetic energy, half mv² of the motion of a typical particle. Some are moving left, some are moving right, up, down, whatever, but on average this is going to be equal to that. So if we set 3/2 kT equals half mv², rearrange, we find that the velocity is going to be roughly root 3 kT over m. Now what's the mass of an air molecule? I mean, air is mostly nitrogen, and nitrogen is diatomic at normal atmospheric conditions. So a typical molecule has 2 nitrogen atoms. Nitrogen has an atomic mass of 14, so it's got 14 nucleons, protons plus neutrons in each atom. So the mass of a molecule is going to be about the atomic mass unit times 14 times 2, because it's a diatomic molecule, which comes out as about 4.6 by 10 to the minus 26 kilograms. Now if we plug this in for room temperature, 300 Kelvin, we find the typical velocity of air is about 500 meters per second. 500 meters per second. That is fast. That's 1,800 kilometers per hour. That's the speed of a rifle bullet. Pretty fast rifle, in fact. So it's actually rather amazing. As you sit relaxing with a bit of physics reading, the air around you is whizzing around at bullet-type speeds. We're probably beginning to sense why it is that nanotechnology is quite hard now. If you imagine something tiny, a component made of atoms that's atomic sized, you're being constantly pelted by more molecules going at these sort of speeds. That's going to do a lot of damage.